Right, a warm welcome everybody. Another great morning. Wednesday has come round yet again for one of Mesh Energy's infamous Wednesday webinars. Great to have you guys on this call. As I said to the people who joined early, we had almost 190 people sign up for this particular webinar. So great to see this this particular topic setting alight the people's interest. This is actually the second time that we've given this presentation. The last time was probably maybe 6 or 8 months ago. And I can tell you we didn't have that many people on. So really looking forward to this one. Just by way, before we kind of get into this and do a bit more introduction, just by way of etiquette, if people can, feel free to turn your videos off, as well as your mics. If you keep your mics on mute, that obviously cuts down any unnecessary background noise and make sure that people get the most out of the webinar experience. We are recording this webinar as usual. By the end of the day, we'll have this up on YouTube so you can watch again if you have to dip out. And do feel free to ask questions as we go through in the chat box. I can see a question already from Demi asking if this is going to be recorded. Yes, it is. Feel free to put your questions in the chat box and we'll go through those at the very end. So we'll get through the content and then we'll go through the questions at the end. And I'll try and keep the presentation to kind of 45 minutes, absolutely tops. So we've got a good kind of 15 minutes at the end for questions. So this week around, we're going to be talking about embodied carbon. And in particular, there's a lot of discussion being had about embodied carbon. And one of the difficulties is kind of bringing embodied carbon to life on your projects and kind of what it means. So we actually wrote this presentation, which has a more kind of practical element. And as you'll see, we've got some numbers in here. We go through some kind of meaningful construction methods for domestic buildings, but these could be applied to commercial buildings in some cases. And actually put some numbers against that. You'll see in the early slides here, we also reference RIBA 2030, which is a popular framework, but also focuses our mind on that relationship between tackling embodied carbon, but also making sure that buildings are kind of warm and cozy enough and operational energy is kept to a minimum. And as we'll see, that's a kind of a battle that is constantly fought as we try and reduce embodied carbon, but keep buildings warm at the same time. But before we go into that, I just want to do a very, very quick intro for those people who aren't aware of what Mesh Energy is about. I'm just going to do 30 seconds on this. So we are an independent and holistic renewable energy consultant. Predominantly, we're working with architects and design teams for private homeowning clients, for business owners, for anybody really on any building of any scale. And fundamentally, we're here to help you guys understand sustainable strategies, help you set sustainable goals, design systems. We can offer full MEP as part of our package and really act as a guide and a partner through the sustainable design process, such that your chances of success are as high as they possibly can be. And of course, like any good consultant, we're trying to make sure that we pack in bags of value there in relation or in proportion to our fees, and we save you more money than you spend with us. That's a really quick whistle stop tour of what we do. Do check out the website, mesh-energy.com, for loads more information. And what I want to finally say before, again, we get into the nuts and bolts of today's presentation is Meshwork. If you've been on these presentations over the last 4 weeks, we've been building up to this. In fact, the vast majority of you as of today will have received an invite to join this platform. So this is a community that we're building, which is all around sustainable building design, education, and really a place to kind of get together, ask questions, share projects, and collaborate with others to really make sure that you learn as rapidly as possible and you find the right people to work on your team. So we're facilitating an education platform here, which as of the 7th of April will be launched to everybody, but until then it will be people who attend the webinars. And Rhiannon's just put the link up there to the Meshwork in the chat box if you want to follow that and register your interest. So without further ado, let's get to the content for today. So we're just really briefly going to cover the RIBA 2030 targets again. We've done whole webinars on RIBA 2030 climate challenge targets. So that's not going to be the focus, but it does set the stage. And then we're going to be talking about this kind of battle between operational energy and embodied carbon. And then we're going to actually spend the bulk of the presentation going through roof, wall and floor constructions, from very, very traditional to, dare I say, kind of quirky and not mainstream, and showing you how that affects operational energy or U values and embodied carbon. The whole point of these webinars is they don't get too geeky, it's digestible content, but we actually leave you with some kind of meaningful information that you can use as a reference, and at the very least gets you thinking to ask better questions. And that's what we hope this presentation will do over the next kind of 40-45 minutes. And then we'll wrap up with some kind of key takeaways for you guys. And as I say, we're recording this presentation. We'll also send the presentation out to your email if you've registered for this. So by way of a really, really brief overview, I'm going to focus on two bits of the RIBA 2030. For those who don't know, the RIBA 2030 Climate Challenge is made up of 4 modules. You've got operational energy, embodied carbon, potable water usage, and health and well-being. And for the sake of this presentation, I'm just going to focus on operational energy and embodied carbon, because when you're talking about building fabric, those are the two that are affected most. So operational energy is talking about regulated components and unregulated components, so stuff like heating, cooling, hot water, fans, pumps, lighting, and then unregulated bits like IT equipment, electrical appliances, and those vary depending on how the building is being used. So operational energy, as per the framework, by the end of the decade, they're looking to reduce that by 75% compared to today's levels. And embodied carbon, that kind of the definition of that is the carbon footprint of a material at a very high level. It considers how many greenhouse gases are released through the supply chain. It includes everything from extraction all the way through to processing, transport, assembly on site, in use and replacement on site, and then end of life as well, and recycling and demolition. And the targets for the RIBA 2030 here, depending on the commercial or domestic targets you're going for, are a reduction of 50 or 70% compared to, again, today's embodied carbon levels. If you've dropped onto more recent webinars, there is a lot of work being done on embodied carbon. There's a bit of a disconnect between what the RIBA, what the Greater London Authority, and what a couple of other bodies are saying embodied carbon levels should be, and we're hoping for clarity on that in the next few months. But embodied carbon is that's the brief kind of definition, and as I say, we've done entire webinars on that. So if you want more information, feel free to check out our YouTube channel. And for domestic buildings, this is a quick overview. Don't get lost in the numbers, but this shows, well, not so current benchmarks, but where building regulations are, and then going through the decade in orange, light green and dark green, they're the various targets for operational energy and embodied carbon. And these are just getting tighter and tighter and tighter. And this is taken right from the straight out of the RIBA, the RIBA kind of document that was put together a year or so ago about this. So this is all kind of widely available. So the challenge here, before we kind of get into actual construction, the challenge here is what happens to operational energy or embodied carbon when you try and make buildings cozier, and vice versa. What happens when you try and reduce embodied carbon and the effect that that has on the U values of a building? They are intrinsically linked because of the properties of materials. And we've shown this slide before, and this is a really kind of, not quick and dirty, but this is a kind of a reliable guideline on what has to happen with U values and various technologies as you go through the RIBA targets. So the first 5 lines there cover U values for key external elements in a building, and then we've got air tightness mentioned there as well. And as you go through the columns, you can see that the U values are getting lower and lower and lower and lower. And funnily enough, when to get U values lower, often walls get thicker, or we use increasingly higher performing materials. But as we'll see, there is a pretty direct correlation between higher performing materials and thicker walls and rising embodied carbon. So one of the challenges that we've got over this year, next year, the remainder of the decade, is how do we reduce operational energy, and at the same time reduce embodied carbon, it would be very easy to imagine a bit like a seesaw where you reduce operational energy and your embodied carbon rises. That would be simple. That's what is happening really day to day at the minute. And vice versa. If you were trying to reduce your embodied carbon, but your U values of your building didn't matter if they got slacker, that would be easy as well, because you could go for really, really, really low natural materials. And if you took nothing else into consideration, your building would perform very, very poorly. But the challenge here is when you're trying to drive down operational energy, you're trying to improve your U values and your walls are getting thicker, or your roof is getting thicker, or your floor is getting thicker. And that has an effect on the spatial result, or the space that you're left with, the volumetric volume that you're left with in the building. But also, as you try and drive down operational energy, invariably there is more renewable technologies that need to be added into the mix as well. So paradoxically, as you add more ground source heat pumps, more solar panels, more wind turbines, more MVHR systems, machines have a huge amount of embodied carbon in them. And so as you add renewable technology, your embodied carbon goes up as well for the whole building. I guess the something to bear in mind here, and we've talked about this before, is the simplicity of building design. And if you can get passive ventilation working for you versus putting in an air conditioning system or an MVHR system, you can see that one would be far lower in processing and materials versus the other. And a lot of people jump to renewable technology to solve problems, but it has an adverse impact on embodied carbon. And on the embodied carbon side, the problem we've got here, as we've mentioned before, as you try and reduce embodied carbon, often the materials that you're looking at are thermally more poorly performing. And so your walls, your roof, your floors get thicker. But also one of the other things which isn't always considered is some more natural materials are not so mass produced as petrochemical materials. And that increases the cost of those materials. So you have a reduction in their thermal performance, but like for like, they actually cost more. And that's a sweeping generalization, but that is an effect that you see. So balancing all these things and finding those sweet spots to enable you to drive down operational energy and embodied carbon is really the skill here as you get more and more involved in the building. And as you can appreciate, and as we've seen on projects, if you forget about embodied carbon and just focus on U values at an early stage of a project, you can very quickly get into some deep and tricky water when you then try and fix a growing embodied carbon problem as you analyze that further on down the project. And in some cases, you can't get that back. You can't recover unless you fully redesign the building or stop, go back into planning, do all kinds of pretty drastic things. And this was a graphic that I pulled up again maybe 9 months ago. And I think it is helpful just to simplify this. There are thousands of materials with what we call EPDs, which are these kind of third-party environmental product declaration tickets against them. But if we just look at a general trend here, this is on the right-hand side of this diagram, we've got thermal conductivity. So if you're right down at the bottom, that is super good at making sure energy doesn't travel through it and resisting temperature change. And then embodied carbon along the bottom. So if you're in the bottom right-hand corner of this diagram, you have really, really low embodied carbon, but actually really resistant to movement of energy. And if you're in the top right-hand corner, you're super conductive, but actually there's often a lot of processing that goes into making those materials. And you can see here, I've clustered these into types of materials. So probably not unsurprisingly, in the top right-hand corner, we've got metals. That's why we use them for cabling, conductive stuff. That's what they're great at, but there's a huge amount of energy that goes into those. And in the other extreme, we've got sheep's wool, sheep straight off a sheep's wool straight off a sheep's back, straw bales, raw clay, earth bank materials. And in between here, we've got, kind of cellulose insulations, wood materials, and then you get into plasterboard, OSB, cross-laminated timber, and then in between that and metals, you've got concretes, clay that have gone through furnaces, tiles, those kinds of things. So hopefully this helps you kind of figure out in your mind how these things relate to one another. And we've got PIR insulation actually that stands out there as a kind of a lonely element, which is great at resisting energy transfer, but is kind of middling as far as embodied carbon is concerned, and obviously uses a lot of petrochemicals as well. So this was really just to kind of help you classify and cluster some of these materials. And if you look at materials, and again, I don't want to get super lost in the detail here, and this is showing you the kind of the general trends of materials. If you compare materials based on their thermal conductivity, this is the kind of list that you end up with. So you end up with PIR, rigid insulation at the top, and then you've got kind of EPS insulation, then actually sheep's wool, acoustic insulation, and as you go down, you get into woods and various things like that, which are more conductive of energy. So that's one list. If you have another list, which is just based on embodied carbon, these things get mixed around. And ideally what you're trying to do is have the same materials at the top of these lists. So these tables show you when you focus on thermal conductivity and when you focus on embodied carbon, how the materials kind of compare to the relative other materials in the list. And it's a really kind of quick and dirty way of finding out potentially which ones have the lowest thermal conductivity and which ones have the lowest embodied carbon relatively, is by multiplying these two numbers. Now, the mathematicians in the room will probably be swearing at the computer right now, but a really, really simple way is just using a product of these two numbers. And so what I've done here is put a table together which kind of smashes together low thermal conductivity, or the thermal conductivity value, and the embodied carbon value. And so this kind of gives you a quick and dirty idea of materials that relatively are good for low embodied carbon and thermal conductivity. And you'll see here, this is a kind of a hybrid list. Obviously every product is different, but I thought I'd just show you this to, again, get straight in your mind how these things compare. So for example, PIR insulation has fallen right down the list here, even though it's very thermally well performing, it's very poor for embodied carbon. But sheep's wool is actually tops the list. It's very low in embodied carbon, but relatively it's actually quite good thermal conductivity wise as well. So these natural materials are surprisingly high up in the list, and the ones that you're more familiar with, fall further and further down the list because they're particularly poor for embodied carbon. So as we get into the detail of different construction examples here, all of these follow a kind of a similar pattern. I'm going to start with roof construction examples here. And what I'm going to cover is three different construction methods. We'll cover what those are for clarity. And then we've got a kind of a summary table, and we can walk through that. And that shows some really interesting trends between, as you try and tighten your U values, what happens with the embodied carbon as we move from more traditional to dare I say, kind of more variant roof, floor, and wall constructions. So the three that we're going to be talking about here are like a standard pitch cold roof with, say, mineral wool insulation. We've probably plenty of those have got those in our own houses, or have been in a house with that. Pretty standard stuff. And then we've got a pitch timber warm roof with PIR in the between the rafters or joists. And then we've got a pitch timber warm roof with natural insulation. So you swap out PIR for natural insulation materials. So here's a pitch cold roof, nothing particularly fancy there. We've got all the kind of the makeup of the roof, which is pretty traditional. We've got the tiles and PIR insulation between and below the rafters, actually. To make sure that we meet these U values as we go through. And then we've got, same thing again, but we've got kind of bats of natural insulation rather than PIR in there. And The other thing to consider here as well as kind of pitch roof alternatives are flat roof alternatives. So just from a materials usage point of view, it might be, or hopefully it's obvious to you guys that whilst this may not be spatially the right thing to do in every instance, flat roofs use less material than a pitch roof does. And because you're using less materials, that allows you to reduce your embodied carbon amount, but also it reduces the heat loss from the building because your square area that you're losing energy from is reduced. It also increases biodiversity and the opportunity to change from more traditional roof coverings. Although we've kept with tiles here, of course, you've got the opportunity for wood shingles, slates, more kind of natural products, which you can think about in the mix. But to keep this simple, I've kept with these, kind of traditional roof construction methods. Otherwise, you just kind of get lost in the data. And to explain how this table works, and this is the same for all the other tables that I'm going to put up here, we've got where we are today with building regulations. We've got the target U value for building regulations, so kind of a nominal U value. And then we have the 3 different roof types here. And what this is showing is at the moment, for building regulations, if you are hitting 0.13 as a U value, generally speaking, when you add up the thickness of all the materials that are contributing to that U value, how thick is the roof? So in the pitch cold roof case, you've got something which is 340 millimeters thick, just using glass fiber, wool, tiles, usual stuff. But when you add PIR into the mix, and that's in between the roof joists, your thickness of your roof structure reduces by almost 150 millimeters because of the increased performance of the PIR insulation. And if you go that route but use natural insulation products, you can reduce, compared to the pitch cold roof, you can reduce the buildup by 22 millimeters. So there's a big jump here between PIR and natural materials. So that's where we start with today's building regulations. As we go through to RIBA 2020, and I've used the RIBA stages here as a kind of a roadmap, we've got a similar U value that you can hit to meet RIBA 2020, and the numbers are the same. As we get to RIBA 2025, you do need to start tweaking your target U values down to around about the 0.2 mark, generally speaking. Your pitch cold roof would increase by about 25 millimeters on this kind of benchmark 340. And as you can see here, relatively speaking, you save even more by putting PIR in the roof, and you have to put a bit more proportionally a bit more natural insulation in. So your saving isn't quite so much over what you'd be doing with a pitch cold roof. And then this is where it gets really interesting, when you really do have to screw down the U values for say a roof makeup to say about 0.1. So you've reduced the U value of that roof element by about 30%. You have, if you stuck with the cold pitch roof, you'd have to add about probably another 75 millimeters of glass fiber. If you have PIR in there, proportionally, again, you've got a massive saving there over the cold one of about 190 millimeters. And you're there or thereabouts. As you use natural insulation compared to your pitch cold roof, you're going to have to put a hell of a lot of natural insulation in to keep that roof warm down to that level. So again, without getting lost in the numbers here, and given that we're talking about embodied carbon as these things get tighter, when you get to RIBA 2030, until you look at the embodied carbon values, it is not clear which one you should be doing. So for example, before I show these embodied carbon values here, you would say, well, why wouldn't you use PIR in a roof construction? Certainly if I've got to get these super duper low roof U values, it's obvious, let's just keep using it. But that doesn't tell the story of what's happening with embodied carbon. So you must look at these two things together. So when you do, what this is saying is, and how these numbers relate here is, compared to the pitch cold roof using traditional materials, glass wool fiber, if you use PIR, your embodied carbon, relative embodied carbon value for RIBA 2030 has gone up by 33%. So your embodied carbon story has got worse. But if you look at the natural insulation or cellulose products, your embodied carbon has dropped by almost 40%. And this is why you cannot just focus on U values of elements. You must always check the embodied carbon impacts. And yes, you might have to make compromises. In this particular case, it will be with the thickness of the roof. But if you have to target embodied carbon and operational energy usage, particularly against the RIBA framework or any other, those two go hand in hand, and you cannot design based on one of those factors alone. So the same thing again, when we look at wall construction methods here, the wall that we're going to look at is standard brick and block, kind of partial cavity fill with bats of insulation. We'll then look at a timber frame and brick construction, rain screen and timber frame construction, and then a CLT construction. And then right at the kind of the, dare I say, the kind of the quirky end is kind of hempcrete and external render. So that covers the full spectrum of what a lot of people easily understand to something that they've probably never built in before. And we'll do exactly the same analysis here. So this is the rain screen and timber frame construction that we've assumed here. I'm not going to go through the detail of this, but pretty standard stuff. We've got rain screen with a CLT structural member on the inside. So you've got your CLT, your insulation, a membrane, and then bats and your rain screen. And then we've got kind of hempcrete and a render solution at the kind of far end. So we've got 5 different scenarios here. And again, it's fascinating to see how these all compare as you increase your U value and what happens with the embodied carbon. So this is where we start. At building regulations, again, we've got a brick and block wall, partial fill, which might be 360 in full construction depth. As we go down these, interestingly enough, the rain screen and timber frame makeup, I think that assumes that's got PIR in. Actually, you're saving 75 millimeters on a standard kind of brick and block construction. Hempcrete is thicker walls by a couple of inches, and rain screen and CLT is a marginal saving there of 20 millimeters. So you get a kind of a flavor of what's happening there. And again, as we go through the targets here, there's a massive jump in what's happening with the hempcrete and lime construction. So you've added another 100 millimeters to your wall construction there. The others are affected, but they're kind of catching up with more standard brick and block construction. These numbers are getting smaller. Your rain screen and CLT wall thickness is almost identical to your brick and block partial fill. What I've done here for those eagle-eyed of you, even though the U values come down here, what we've done is gone to a full fill wall here rather than partial fill, and that's why the width of the overall construction hasn't got any thicker. You've just filled that in with insulation. And as we go through here, then you put more and more insulation in your standard wall and that gets thicker. But now our numbers in red here, so green is the construction is thinner or less invasive than your standard brick and block construction here. The red ones mean that your wall construction is getting thicker than the traditional construction that we've chosen here. And as you get to RIBA 2030, when you've got wall values of about 0.1, 0.11, you can see how much thicker the hempcrete and lime walls need to be when you're at the far end of the spectrum. But even rain screen and CLT has to be another 80 millimeters thick, typically speaking. If you stuck with traditional construction, that wall might be another 50 millimeters thick. And the timber frame brickwork is pretty much bob on what brick and block would be. So this is more challenging. This is more challenging. If you're fixed with you've got planning permission for a gross floor area, you might be scratching your head here when you're looking at other methods of reducing your embodied carbon. But again, to get the full picture here, you need to have a look at both. So when we look at the RIBA 2030 far end here, I've compared the embodied carbon to brick and block construction. And you can see here that using timber frame, a lot of people would gravitate to timber construction as a way of reducing embodied carbon. So timber frame and masonry has come down by about 28%. So there's an embodied carbon saving there. Rain screen and timber frame construction is a whopping 85, 87% reduced, which is a big win there. When you look at CLT and a rain screen, it's slightly less impressive, but still a reasonable 70% reduction. But interestingly enough, the hempcrete and lime, which you might expect to be blowing the competition away, because of the sheer quantity of material that you have to use in order to hit that U value. You've used almost the best part of another foot of 250 millimeters, or the best part of a foot of wall thickness there. The sheer volume of material has counteracted the embodied carbon benefits. So here, if you were to look at this, you would start looking at rain screen with a kind of a timber frame construction to make the biggest impact for the least dimensional impact on the construction. Again, just a fascinating insight as to how you've got to keep your eye on both of these things. And I think what this does highlight is when you're looking at your methods of construction for all your key elements of your building, you must do this kind of analysis before you pick one, because you could be quite quickly backing the wrong horse, particularly as you get into RIBA 2030. And then kind of finishing up with kind of floor construction and looking at that, we've got three, I think, different constructions here. We've got a reinforced concrete raft with EPS insulation. We've got block and beam floor with concrete blocks and screed. And then we've got a block and beam floor with EPS infill blocks and a recycled screed. In both the block and beam floor examples, those latter two, I haven't, but because of the various things in the ground and issues that people can see, I've factored in a bit of concrete footings, but invariably your biggest variable might be here the amount of concrete that you've got to put in the ground. So I appreciate there may be some bigger unknowns here with the embodied carbon. But we'll talk quickly after I've covered this off about your concrete alternatives. So here are the constructions, a pretty standard concrete raft with EPS insulation. There are a number of companies and houses being built to this construction now. Really good for passive house and getting some very low kind of slab U values. The alternative is good old-fashioned brick and block and beam with insulation over the top of that, and then underfloor heating and kind of screed, and then your floor finish. And your alternative to that is using a kind of a recycled underfloor heating screed. And you can get these kind of EPS infill blocks as well, which are lower carbon and a kind of structural, structural insulation, I believe. So those are three that we're going to be looking at. Floors are really tricky, because more tricky than any of the other elements, because the amount of load that these things have got to take and the role that they play is fundamentally different from the walls and the roofs in some cases. So it is really tricky, because there's a lot of load bearing materials that have to go in the floors, and it creates its own challenges. So again, if we look at building regulations here, we've got 0.13, say, for the floors. If you looked at the raft construction, that might be about 360 millimeters thick, assuming kind of EPS and reinforced concrete. And as we look at the other options there, you can get much slimmer floor constructions, say, notwithstanding the footings that have to go in. And again, as we go through the various targets here, not a great deal changes, but as we get to the tight end of RIBA 2025 and 2030, you get some, these other construction methods compared to a raft floor are less invasive, I suppose, as far as thickness are concerned. But generally speaking, there's not much change across the board. But the embodied carbon, again, is worth looking at here, because you don't get the full picture unless you take that into account. So block and beam, really, with PIR insulation is really no different. There is a slight saving there, but as I say, once you factor in the concrete footings, that might wipe away that saving. Compared to a reinforced concrete raft, there's kind of much of a muchness. So sticking with a traditional block and beam floor, there's nothing really to be gained. When you look at block and beam, though, with these kind of structural EPS infill blocks, there is a greater saving to be had here. And I mentioned that I would talk about footings. So one of the potential biggest savings here is in the concrete footings. As you get away from raft constructions, concrete is still, classed as an evil villain when it comes to embodied carbon. But great strides are being made in reducing the carbon impact of concrete. And I would strongly suggest that anybody takes a look at GGBS concrete, which stands for ground granulated blast furnace slag concrete. So essentially that's a recycled product. It's used, slag is obviously a byproduct of manufacturing processes, and using that in there as the aggregate makes a big difference in the embodied carbon in concrete footings. And I think it is becoming more and more available. Invariably, there'll be a price premium with it, but if you're looking at embodied carbon, that can be used as a really powerful replacement for more traditional concrete used in footings. So the floor slab is a bit more boring there. It's not as exciting as some of the other constructions, but is there for, I guess, telling the overall picture. And I guess to kind of sum up here, you need to have a look at how your U values are being affected and your embodied carbon. And just taking a really general example here, a house that may traditionally have a cold pitch roof with brick and block wall construction and a concrete raft floor construction with PIR, just making some simple changes, making that a warm pitch roof, changing to brick and timber frame, changing to block and beam with an EPS infill insulation, massively, probably by about 30% reduces the embodied carbon of that construction, generally speaking. But better than that, so you've reduced the embodied carbon, but actually the walls are thinner, the roof construction's thinner, the floor need be not as thick, and so you get more room for lower embodied carbon. And this epitomizes the opportunity here. If you do the proper analysis at the right stages of a project, there are win-wins to be had here. You haven't got to make compromises all the time, and you'd be far better informed about the methods of construction that you want to go ahead and take a look at. The other great thing is the information that I've just shown you guys is fully accessible by you, and you can do this. You don't need me or my team to do this at these early stages, and I'll cover off how you do that shortly. But the key takeaways here are that RIBA 2030 targets are tightening considerably by the end of the decade. And if you are designing to those targets today or in the very, very, very near future, you must get your head around what happens to U values and how embodied carbon is affected, and getting your head around methods of construction and risk-free methods of construction to make sure you tick those boxes as the bar gets higher. Embodied carbon and thermal performance improvements need to be balanced. I've said that over and over again. But what's fascinating is small changes in construction methods can dramatically reduce embodied carbon. We're not talking about tearing up what you know. It's just digging down a bit deeper and knowing what your options are, or some clever material selections that you can make that can have a big difference. And finally, as I've just said, this isn't about radical change. This is just about intelligent, thoughtful change, which can come about almost effortlessly by changing your design process and focusing on this earlier on in the design stage. And I said to you guys that these numbers are available to your practices. And that is you can do that by using our embodied carbon calculator. All of the values that I've presented in this presentation, I got from our embodied carbon calculator. You can download this from the website. We're on version 4.0. I've put the URL here for the embodied carbon calculator. I'm more than happy to say Field and Clay Bradley Studios has a free embodied carbon calculator as well, which is Excel based. And it's a free country. Do check theirs out. Do check ours out. We have different kind of takes on it, but the numbers are pretty much like for like, because the methodologies are and the materials that we're using are identical. So do check out our calculator. We've got various videos on how to use them as well on our YouTube channel. And do play around. As you get more serious looking at embodied carbon, we're always here to support you through those further stages, or if you have any questions. So that is it, guys. That is kind of a whistle-stop tour of some of the practical construction methodologies and how embodied carbon and U values affect one another. As I say, it's a massive subject, so hopefully that's given you enough for the moment to take away. I can see we've got loads of questions, so we'll go on to answering some of the questions. As I say, if you guys do have questions, put them in the chat. So Sophia is asking, hi Doug, great seminar as ever. Thank you, Sophia. In terms of material conductivity, you do have more nuances though with some materials. Can you get mineral rock? You can get mineral or rock wool at 0.032 to 0.037. Yeah, that's really important to note that every material, and there are loads of EPDs against materials. There is always a band. There's never just one fixed value. So certainly at the early stages of design, you just need to make sure you're heading in the right direction. You can always tweak the values up and down, but you need to make sure that fundamentally you're heading in the right direction and that you can achieve values with the kind of materials and the kind of wall thicknesses and roof thicknesses and floor thicknesses that are acceptable. But that's a fair point, Sophia. There are, you know, more and more materials getting added every single day, which invariably you can pick from the lowest ones, and you may put more effort into procuring those. And then there are middle of the road ones that you could probably buy from TP and Juicens and all those kind of things. It's just how much effort you want to put into to picking those and selecting those. Charles, so he's saying, I presume sheep like cattle emit methane. Is this taken into account in the low embodied carbon of wool? No, I believe methane production by sheep is not taken into account. It's more about the processing of the materials that is quite a big factor. I mean, it's worth understanding that certainly if any of you are familiar with the kind of the RICS whole life carbon assessment methodology, you have various stages, and processing is a massive part of a material's carbon footprint. So the difference between shearing a sheep and washing it and producing sheep's wool bats, or producing cellulose insulation from paper is far less invasive than you know, PIR, you know, drilling oil out of the ground, creating those petrochemical products and all the processing associated with those. But in short, Charles, no, it doesn't take into consideration methane. David John is asking, with regards to straw bale construction for wall construction, what's the thickness in embodied carbon going to be like for RIBA 2030 in comparison to those shown? Is it more or less? That's a good question. I mean, straw bales are surprisingly good at insulating. I'll take you guys back to the embodied carbon calculator. We have that in the list of the materials that we've got in there, so you can have a play around and compare that with all the other materials that you've seen on there, for the sake of just downloading the program quickly. But straw bales are pretty good. Obviously, straw bales come in fixed thicknesses. So if you can't get the U value that you need from, I don't know, 300 millimeters worth of straw bale, then you probably have to add another one which might be 600 millimeters thick. So they're obviously like big bricks. So you're kind of limited as to more kind of finite thicknesses. It's a bit more kind of lumpy in that respect. Who else have we got here? Yeah, I think that's the bulk of it, actually. Charles, what's Charles saying here? In the same way that battery technology is revolutionizing, say, the electric vehicle market, are you able to tell us anything about innovative, emerging, less hydrocarbon orientated insulation products? Nothing specifically, Charles, but like, you know, innovation in the space of materials will be ferocious. You know, the Greater London Authority is putting a big focus on embodied carbon, and it probably in the next 5 years you may find embodied carbon coming into you know, building regulations and doing analysis for buildings. So there is a huge amount of innovation, and as there's more interest, there's more R&D put into it. But you know, what is really fascinating is products like PIR and concrete, which are very obviously very poor, generally speaking, for embodied carbon. Those industries, concrete is a classic example, have really gone out of their way to market the fact that they're doing more work, they're putting more recycled materials into concrete, and they're actually reducing that embodied carbon, because at the end of the day, if they can't prove that they're making improvements, alternatives will be found, and they will, you know, we live in a capitalist society, so they'll sell less, and that's not good for their shareholders. So there's a huge amount of innovation that's going on, but I can't tell you of any particular massive innovations. But that GGBS concrete is a really good one to look at. James Hall's mentioned about space therm and equivalent thin sheet insulation. They have fantastic claims here. I've seen those, James, as well. At a price, what's the embodied carbon of these high efficiency materials? That's a good question. I haven't done any on space therm particularly, James. I haven't done any particular analysis, but you know, you are going to pay. There's no magic here. As you get super duper thin, you know, embodied carbon and processing will go up. Invariably, there will be kind of standout exceptions to that. But hands up, I haven't had a look at space therm myself, but there are some incredible products that are being marketed. And as always, I would encourage you guys to look beyond the marketing fluff, and to be really sure. I would apply more and more pressure to the manufacturers that you're speaking to about providing you with an EPD for their product. Manufacturers are cottoning onto this. The use of one-click LCA and various other professional products are making it more widely available for EPDs to be uploaded, and they're encouraging that, because then people, funny enough, can get their products specified on jobs. So I would encourage you guys to look beyond the marketing kind of greenwash and ask those manufacturers for an EPD as well. Mohammed, how would the lifespan, recyclability and reusability of a material affect the embodied carbon? So this comes back, Mohammed, to the whole life carbon assessment methodology. And EPDs, although there is some you know, kind of comparison of EPDs that you do, the whole life carbon assessment methodology takes into consideration all of those things that you're talking about there. This isn't just about, you know, digging up raw materials and processing. It's about transport, it's about replacement in use of a building, it's about demolition, it's about reuse at the end of a product's life cycle. And we will see over the next few years more and more products declaring that. Some stuff you can declare, the manufacturers can declare that. Other stuff is more site specific, you know, particular how far you're transporting materials and what the kind of the demolition plan is and reuse plan. So it'd be a mix of various things, but absolutely all of those processes that you're talking about use energy, save energy, and are captured by the whole life assessment method. And if you visit the RIC's website, it's pretty easy to find that whole life assessment methodology on there. And Charles, just a final one here. It would seem that harnessing the recycling materials has got to be the way to go. The GGBS concrete, for example, has superior material properties as well as being lower embodied carbon. Yeah, and as I say, there will be increasingly more and more focus on that. I think the biggest challenge for me is it's pretty easy to work out what the U value is of a particular construction build-up, and our calculator helps you do that as well as work out the embodied carbon. But I think we need a lot more visibility on embodied carbon of materials, and there's a lot of work being done on some of these calculators, but as well as the EPDs and general resources. I know there's I think it's the EC3 database for materials, which is being made available. And I think a lot of the work to be done over the next couple of years is really translating what embodied carbon means in the real world, so people are far more familiar with what a product actually, what its impact is beyond it, you know, being thermally performing, or you know, say having a glossy brochure associated with it. And that's the big struggle for all of us, is just continually learning and trying to find tools and sharing tools that helps us do that. Folks, I think we're out of questions there. As always, I'll leave it another few seconds just to see if we can catch another question. Again, a massive thank you for the turnout on this one. Hopefully you found that useful. We'll stop the recording. We'll get this up on YouTube. And next week, just to wrap up here, it's me again. You're gonna have to listen to my dulcet tones for a whole nother hour. And we're gonna be talking about smart low energy building design. So I wrote a book back in 2019, I believe, on how to design low energy buildings, and a kind of a methodology for that, looking at building the right team together, getting the right strategy together, our energy hierarchy it picks up on, putting the right team together, all kinds of really cool stuff through design, specification, construction, post-occupancy evaluation. I'm going to be sharing those tips and tricks with you, and I hope to see you guys there. So do book on Eventbrite as normal. We'll be promoting on LinkedIn, and look forward to seeing you next Wednesday. Take care, guys. Bye.